Hello everyone. In this video we're going to cover examples from chapter 9, which is all about inferences based on two samples. My name is Fred Rispoli and I'm coming to you from Stony Brook University. In particular, we're going to look at examples involving inferences for means with large samples, inferences for means with small samples, and we'll take a look at inferences involving paired data in example 5. These are chosen based on frequently asked questions by students and frequent errors on tests. We have a roadmap here for hypothesis tests. And you may recall that in chapter 8 we looked at tests and inferences based on one sample. Here we're looking at inferences and tests based on two samples. In this video, we're going to cover this left branch here, inferences involving means. We'll look at large samples, we'll look at small samples. In small samples, we'll look at the equal variance case and an example involving paired data. So when we have large samples, we get a confidence interval that looks something like this. We have the difference in the sample means. This is a term from the normal distribution that you're familiar with. And over here we have the square root of the variance from the first sample over its sample size plus the variance of the second over the sample 2 sample size. So this will be our error term, and we'll subtract this from the difference in sample means, and then over here we will add that. The test statistic for hypothesis testing simply looks like this. We get x bar minus y bar in the numerator. Typically, we hypothesize that the difference in means is 0, but it is possible to hypothesize the difference is something other than 0. So that term would go up here. And then in the denominator, we have the square root of sample 1 variance over m plus sample 2 variance over n. In our first example, we'll take a look at constructing a confidence interval for large samples. So suppose a test is conducted to compare break-in strength of cell phones manufactured by two companies. Summary data is given below. So here you see we have, these are the sample sizes. Here we have sample means. And these are the sample standard deviations. We're asked to construct a 95% confidence interval for the difference of the means. All right, so we just point out that m and n are both large. By large, we mean they're both greater than or equal to 30. We start to set up the confidence interval. So we look at the sample means, we look at the difference, 107 minus 113. That gives us a negative 6. The z alpha over 2 term, again, that comes from a normal distribution. For a 95% confidence interval, alpha is 0.05. So alpha over 2 is 0.025. We want the z value that leaves 0.025 in the right tail and 0.975 in the left. So when we use the table, we find 0.975, and then you could see that this is obtained when z is 1.96. So that's a value that occurs quite often. You probably have it memorized by now. So we get 1.96, and then underneath the square root sign, I have to look at the variance for sample 1. which is 10 squared. Remember, the standard deviation was 10. The variance is 10 squared over 65 plus 13 squared over 60. So when we simplify and multiply by 1.96, you see that we should end up with 4.1 as our error term. Right? This term here involving the square root should simplify to 2.087. Multiply by 1.96, we get an error term of 4.1. So we're looking at minus 6 minus 4.1, so we get negative 10.1. And negative 6 plus 4.1, we get negative 1.9. So a 95% confidence interval for the difference in the means is minus 10.1 to minus 1.9. In example 2, we're going to take a look at a hypothesis test for the difference of two means. And again, we're still looking at large sample situations. So suppose a credit card watchdog group claims there's a difference in the mean credit card debts of households in New York versus households in Texas. The results of a random survey of 250 households in each state is given below. So in New York, we see sample mean 4,446.25. Here's our standard deviation. We know sample sizes are both 250. Here's the sample mean for Texas. Here's the standard deviation. If you do some sort of eyeball estimate, you could see, well, they're fairly close. A large standard deviation, so maybe you can formulate some sort of guess, but we always need to take a look at the specific values that we get. So these two samples we note are independent. So our question is, do the results support the group's claim? And we're given to use alpha equals 0.05. Okay, so we use our 5-step method. Step 1 is to identify the hypotheses. Notice in the statement we weren't given any indication as to whether one mean is greater than the other or less than the other. So we set this up as a two-sided test. The null is that the means are equal. The alternative is that they're not equal. You may also see this expressed in terms of the difference. Mu1 minus mu2 is equal to 0. Okay, and then this would be mu1 minus mu2 is not 0. All right, and we have the alternative is the claim. Alpha is given to be 0.05. Here's the formula for a test statistic. Once again, our rejection region is based on 1.96. This will be the z-value that leaves 0.025 on both the left tail and the right tail. So that would give us our 0.05. In step 4, we substitute in the values. So here we have the two different sample means. These are the sample standard deviations. We have to square these, divide by 250. Do the same thing here and then add. So this whole fraction should simplify to minus 1.11. You may want to pause the video and practice that. This is good practice. Have to be careful when we work this out. I would say keep these values at least to 4 decimal places while you're working these out. So we get this rounded off, we get minus 1.11. So this would have an absolute value that's less than 1.96. So we are not in the rejection region. So we do not reject the null hypothesis. A summary statement might be that the data does not provide evidence that there's a difference in the credit card debt. Now, what about the p-value? Well, in a two-tailed test, we need to find the p-value we get from our z and then multiply it by 2. So we're looking at 2 times the value we get from the table, where z is negative 1.11. Let's take a look at our table. So at minus 1.11, you can see we'd be in this row, this column, we get 0.1335. So that's the value you see here, 0.1335. We double it. We get a p-value of 0.2670, so that's quite large. It's greater than 0.05, so we do not reject the null. This confirms it. And so here you can see statistically our conclusion is that these means are roughly equal to each other. Next, we'll take a look at inferences for the mean and differences for the means, where we have small independent samples with equal variances. You may remember in chapter 8 when we had small samples, we used a t-distribution, okay, and we'll be using a t-distribution here as well. But there's a new consideration here. We have two different samples, so there are two cases that people look at. One case is when you have equal variances, which is what we're going to look at here. The other case would be unequal variances. But when we have equal variances, we have this new term to consider that we'll call a pooled variance. And you can see that this term here, which is denoted by SP, is given by m minus 1 times the variance of sample 1 plus n minus 1 times the variance of sample 2 all over m plus n minus 2. So you'll see this term in our formulas. If we think about constructing a confidence interval, we start out as before. We'll have the difference of the two sample means. Then we have a term that comes from a t-distribution. Notice the degrees of freedom, m plus n minus 2. So we add the two sample sizes and subtract 2. And we have this alpha over 2. And then we multiply this times the pooled, well in this case it's the pooled standard deviation. We would calculate this and then take its square root times the square root of 1 over m plus 1 over n. Okay, so that's our formula for confidence intervals. So here we must have both m and or n less than 30. So if either is less than 30, then we would use this approach. When running a hypothesis test, notice the test statistic. We have the difference in the sample means in the numerator. In the denominator, you have the pooled standard deviation times the square root 1 over m plus 1 over n. All right, let's take a look at an example. Total dissolved solids, which we'll abbreviate as TDS, is a measure of water purity. Suppose researchers measured the TDS level of water samples from random locations in each of two lakes, and the data is given here. So in Lake A, they took 10 different samples, and in Lake B9, these are the sample means for TDS, and these are the sample standard deviations. Assuming equal variances, construct a 99% confidence interval for the difference in mean TDS levels. All right, so we note m and n, they're both small. We're going to assume an equal variance. So we find our pooled variance here using the formula. So we would work this out. All of this was given. This works out to be 538.4. Remember, that is our pooled variance. We will need a pooled standard deviation later on in one of the later calculations. The value we get from the t distribution, okay, you may remember we were given alpha is equal to 0.01, right? We know that because we have a 99% confidence interval. So 1 minus 0.99 is 0.01, so that's our alpha value. For confidence intervals, we need alpha over 2, so that gives us 0.005. Degrees of freedom is 17, right? It's m plus n minus 2, so 19 minus 2 is 17. We have to go to the t distribution. I have the table here. So we find degrees of freedom here is 17. We know alpha is 0.05, so we come over here. Alpha is 0.05, so we should get 2.898. Okay, so that's our value here that we'll use in the calculations. So constructing the confidence interval, I start out, I take the difference of the two sample means, 108 minus 97. This is the term I get from the t distribution. Okay, over here we have the pooled standard deviation of the SP. Notice it's the square root of this value that we calculated up here. And then I have this term, 1 over m is 1/10 plus 1 over n 1/9. So when we simplify this entire term, we should get 30.9. You can see the difference in the means. Easy to see that that's 11. So we get 11 plus or minus 30.9. So a 99% confidence interval for the difference is 11 minus 30.9. We'll get negative 19.9. And 11 plus 30.9, we get 41.9. In our next example, we're going to take a look at a hypothesis test for the difference of two means, where we have small samples, and again, we'll look at the equal variance case. So suppose that in a study on the healing process of bone fractures, researchers observed the time required to completely heal a bone fracture. Let's say these studies were carried out with rats. 10 rats were randomly divided into two groups of 5. No treatment was done to one group, we'll call that the control group, and a medical treatment was done to the other group, we'll call that the treatment group. The time spent in days to completely heal the fracture for each rat is given below. So notice we have small sample sizes, right? We have sample sizes of 5 for each group. We want to test if the mean duration of healing can be reduced by the medical treatment at alpha equals 0.01, and we're told to assume equal variance. Okay, so as we solve this, we'll start out by, we would have to make some calculations if we had the problem in this form. Notice we're not given sample means or standard deviations, but it's fairly easy to find these. So using some technology, calculator or a spreadsheet, we can calculate that x bar is 32, S1 8.63, and then for the other group we have the sample mean y bar 29.2 and S2 7.12. Now we use our 5-step method. So we want to know if 1, is better than the other. So let's see over here. We want to test if the mean duration of healing can be reduced by the medical treatment. So that leads to this, this test over here. So really, the claim would be over here, and we would be testing to see, does the control group take longer to heal than the medical treatments? Okay. Remember, we want the heal to take place as quickly as possible. So we make this our alternative hypothesis. We could think of the null as mu1 is equal to mu2. Could also express this as mu1 less than or equal to mu2. We're given alpha. Alpha is 0.1. Okay, again, that was given. Let's just confirm that. Here I see 0.01. Let's take a look here in the solution. This is written up as 0.1. So let's assume alpha is 0.1. We'll calculate the pooled variance here. So our pooled variance would be 4. Right? Remember, m is 5. We have this over here. 8.63 squared. We want a variance here. Plus 4, 7.12 squared. Over 5 plus 5 minus 2. We get 62.59. The test statistic formula looks like this. We have P is x bar minus y bar over the pooled standard deviation, square root 1 over m plus 1 over n. When we look up our value in the t table, we have to realize the degrees of freedom is 8, 5 plus 5 minus 2. So we could find our rejection region. Okay, we have to think in terms of our test. So here we need the value p.1 with 8 degrees of freedom. Let's check that out in the next slide. So here I have 0.1, 8 degrees of freedom. So we get 1.397 as a critical value. So you see that value here, 1.397. When we substitute values into our formula for t, we get 32 minus 29.2. So those are the two different sample means. Remember, SP is the pooled standard deviation, so we have to take this value here and then take the square root of that. So this is our SP, square root 62.59 times the square root of 1/5 plus 1/5. So you may want to try to work that out with a calculator. It's a nice exercise. Should get 0.560, which is less than 1.397. So therefore, we do not reject the null hypothesis. So practically speaking, we would say that there is no significant difference in the healing times. The p-value here we could get, you really can't get it using the table because we have our t-value is 0.56. If I look at degrees of freedom, you can't find 0.56 anywhere in here. So we will simply be satisfied here by using a p-value obtained from technology. It would be 0.2954. You could get this using either R or Excel. Okay. Our last exercise will be to study something with respect to paired data. When we have data in pairs, we want to try to group the data. For example, here we have data in terms of families, and we're trying to sort of group these together. This turns out to be a more powerful way of running tests. Okay, powerful in the sense it will lower the standard deviation by looking at what happens sort of in pairs. Typically it's before or after a certain treatment takes place, but pairs can arise naturally in other ways, as you'll see in the example. Now we use D to denote the difference in each pair, and D bar would be the average difference. So here in the formula for confidence intervals, you see a D bar, we see a T term. Now n minus 1 is the degrees of freedom. Here n is the number of pairs. The S is the standard deviation of the differences, and then here we have the square root of n. So our test statistic is simply our D bar, the average of the differences, and in the denominator we have the standard deviation of the differences divided by the square root of n. So here's an example. Some people believe from their observations that the first child is more fluent than the second child in their parents' native language among second-generation Chinese Americans. To test this claim, suppose a Chinese comprehension test was given to 6 randomly selected second-generation siblings in Chinese American families. So the scores are given below. So we have a natural way of pairing this data, right? And it would certainly make sense to pair the data. So in one family, the first child scored 43, the second 42. In the second family, 27. For the first child, the second child, 24. So the question is, does the data support the claim? We're going to use alpha equals 0.01. And then we will be able to obtain bounds from the table for the p-value. So we'll go ahead and do that. So a first step here would be to find the difference in each of these. Now I didn't display that here, but so I'm looking at 43 minus 42, that's 1. 27 minus 24, that's 3, and so on. So we get these 6 values, which are, we'll call them the differences, and then you need to find the average of the differences, and that is where D bar comes from. You may want to stop the video and check that out. Find the difference in each pair, then find the average amongst the differences, should come out to be 9.17, and the standard deviation of the differences, 6.24. Okay, notice our degrees of freedom here is 5 because we have 6 pairs, so our n is 6, n minus 1 is 5. Here's the test statistic. So we just noted D bar over the standard deviation of the differences divided by the square root of n. So our rejection region comes from the t-distribution. We have a one-tailed test or one-sided test. So our critical value is t.01 with 5 degrees of freedom. This comes out to be 3.365. Let's just confirm that in the table. Whoops, I think we have to go up here. So we had 5 degrees of freedom, so we're in this line, and 0.01 is the alpha, so you can see we get 3.365. Okay, so that's where we get this. When we substitute values into the test statistic formula, we get D bar 9.17 divided by 6.24 over the square root of 6. So this simplifies to 3.6. greater than the critical value, 3.365. So therefore, we reject the null hypothesis. Okay. Practically speaking, we would say the data supports the claim that the first child does better than the second. Now, to get a p-value, we want the probability that t is greater than 3.6. So if we are using a table, we would find the line with the proper degrees of freedom, so that's 5. And then we would look for 3.6. We would try to figure out where that is. So a 3.6 would be between these two values. Right? We know it's greater than 3.365, but it's less than 4.032. So we could say that the p-value lies between these two values here. So it's between 0.005 and 0.01. So we could use that to get our bound. That's what I've said over here. P is between 0.005 and 0.01. Right? So the fact that P is less than 0.01 sort of confirms our decision here, right? P is low, so the null must go. So we've done that over here. Now, just for fun, we could sort of confirm what's going on with technology. If we were to do that, we would see that P is equal to 0.0078. So right in this interval, greater than 0.005, but less than 0.01. Okay, so this concludes the video.